Swayam Prabha. Digital India. Educated India.
So I skip one part a little bit, the impulse response. We need this concept again in the later when we talk about the fluid structure interaction, especially impulse damping, radiation damping. Okay, I still want to cover that. After that, today I'm going to teach fluid dynamics, wave motion, and then we talk about random C. In that way, you understand the ocean better. Okay, and now let us come back to learn impulse response first. Okay, and the impulse response, like you have hammer here, you hit that, right? This impulse, and the impulse mathematically, impulse is the force, and this happen at a very short period of time, right? And in this short period of time, then the amplitude can be large, depending on the weight. And such kind of very short period of time, the total area here, and the integrate is F hat, right? So it's only happen at a very, very small duration. And mathematically, and it doesn't need to be square shape, and it can be any other shape, as long as it follows this mathematical rule. Okay, the integration cross that will be totally the momentum, right? The pulse force, the integration. So, and this is impulse, okay. And impulse you can shift a little bit, right? If you shift, then everything get shifted to time invariant. Okay, so let us say this type of impulse, okay. And like when you play pool table, right? This ball hit that ball, and this ball stop now, this ball continue moving. And this is a change of momentum, right? Impulse time t, the duration, this momentum change. This momentum change will give new velocity to second ball, right? Similarly, this can be used for this vibration system. And this vibration system like that, right? Then you give it the impulse. And after you give the impulse, the momentum will change. That means you have velocity jump, right? So this velocity jump, just imagine that way. And if the system is set free at the beginning, after you use the hammer to hit that, and then you will get or initial velocity, right? And the initial velocity like x 0 plus. What I mean 0 plus means right after time become positive, you get a small velocity based on the impulse, right? The momentum change. So this type of thing, and you can using the relationship. Let me see why it's like okay. Using the relationship, right? And you can get the so-called impulse response. The response of a certain at the initial condition under the impulse force, right? It's like this one, and usually we use the call this as the impulse response. Okay. So the impulse response, you can solve this using the equation we learned yesterday. We give initial velocity, initial position, you can solve that. Okay, so it's a vibration system like that. You give the impulse force, that is response, right? And this response, you can convert such kind of impulse response as vibration response to the initial condition, where the initial condition, this impulse momentum change give the initial velocity, right? So, eventually we get this response, right? Given the unit impulse and the certain response like that way. So this impulse response ht, okay, and ht is time invariant. That means if the impulse happen not at zero, shift at time tau, the response, everything shift at tau time. So now, and given this, we can get an arbitrary input, the response to the arbitrary input. Just imagine that way of force, arbitrary force in the time domain, Ft, and this T. You take this force as or not a small impulse, you add them together. Each impulse is this amplitude times small delta t here, right? F, this at ti, and time delta t, this impulse or amplitude. Then this also the time shift, right? And it happened not at exactly 0 time, it happened at the ti. So here, this response for this impulse at fti. So if you have such kind of impulse, you add all the things together. For example, here, this is T1, T2, T3 is T Ti. So you add them together, then become integration, right? And that is a convolution. So that overall, such kind of expression is the arbitrary force input, right? Ft, arbitrary force input, convolution with the impulse response, then you get arbitrary output. Such kind of relation can be used for any linear system, like ocean wave system also, right? And basically, that's the convolution for arbitrary force input. And if you know the impulse response, you can use the convolution. Okay, so and this convolution initially is discovered by Duhamel. This is why it gave this name for any vibration system, right? This is for single input, and you know the impulse response, you know the arbitrary force input, you get output. So, and let us continue and change this slide today and talk about fluid. Okay. Fluid, ocean wave, and or the well as a random sea. Okay. And there are two parts. And before the coffee break, we talk about fluid basics and then wave theory, wave motion. And after that, we talk about random sea. And this natural slides look like we cover both. Actually, we are going to pass in between, then continue. Okay. So, and as I mentioned that we talk about fluid dynamics, and in this fluid dynamics, if you want to read more, you can read this book, right? And then we talk about wave motion, hydrodynamics part, and some good content is in these two book, actually 3 book, and then random sea. And after that, when we talk about wave WEC modeling, wave energy converter modeling, mostly we refer to here. And this is a reference in this nature. And I take some pictures from this book too. Okay, so talk about fluid, right? We understand that some of students are in the sophomore year, right? You may not learn fluid yet, but you must already learn the solid mechanics, right? Solid mechanics, what we learned, right? The Newton's law, you have strain, stress, right? And like this bar, you push that, and you have a stream, and this stress relationship that follow Young's modulus relationship, like E, this Young's modulus. You may have shear stress too, right? Shear stream and this angle change. And now for the fluid is in another way. And if you have plate move at velocity u, right? This plate is fixed, right? Then this is shearing. This is the angle change. This is beta, right? And at the small angle, beta will be the distance. This is delta A divided the thickness of the fluid be, right? So, and such kind of angle change, right? And if this is just angle change, what we care about is instead of like solid mechanics is about angle in the fluid, angle is not enough. Why? This angle can continue increase with time going on, right? And just think about the shear and the continued motion, right? So we care about the rate change, right? This is small angle divided by the time. So that is shearing strain, rate of shearing strain, right? And such kind of rate of shearing strain, and we write as gamma dot way, right? Is velocity divided by b. So, and this will give your force, right? So this shearing force, and it's different. That is a function of the shearing strain, right? Rate of shearing. Okay, so this is the Newton's flow, right? And this is again is approximation. And this mu, this constant doesn't need to be constant, right? As you can say, that can be function of this force, right? This is mu can be constant. If this constant, this Newtonian flow, right? And if you in the morning you use toothpaste, and the shearing rate and the shear force is more like follow this line, right? And some material you have higher shearing rate, strain rate, then you have different shearing force, right? So I want to let you know that this is this called dynamic viscosity, or sometimes we just say viscosity. This is linear approximation and Newtonian flow. Okay. And another thing is hydrostatic force, right? Hydrostatic force, this you learn in high school physics, right? And it's delta P is rho G H, right? H is height. Okay, and again, this H is relative height, so this is also relative pressure, right? You define where the height is zero, right? So now, and using this pressure and you hydrostatic pressure, and you can calculate the buoyancy force, right? Buoyancy force here is rho G H C, and time cross the C is center, okay, that, and this area, and this is actually you can understand that hydrostatic force is proportional to the volume the water is dissipated, right? Okay, so now about stability. Stability is a very important concept in wave energy side, and or in any floating structure, right? And typically you think, okay, is the buoyancy force center and gravity center, this relationship is buoyancy force center is higher than the gravity center, the certainly stable, right? But it's not always the case. And for example, if you have, this mouse, okay. For example, here, and this is a ship, right? And the buoyancy force center can be below the gravity center. This figure shows clearly like the buoyancy force center and the gravity center, right? The buoyancy force center can be lower, but the certainly is still stable, right? The reason is, and when you like ship that the tilt some angle, right? It generate momentum, restoring force. So help to recover. Same thing is for the offshore wind structure. For example, the spars type of thing typically is a buoyancy force center and gravity center, right? This relationship, buoyancy force center is higher than gravity center. Like a semi-sub platform, and this is called a semi-submersible, and the reason is half is under the water, right? And this is similar as the boat, and the gravity center can be higher than the buoyancy force center. Okay. So, and in fluid mechanics, you guys learn Bernoulli equation, right? I want to let you know what's a Bernoulli equation. Okay, and the Bernoulli equation actually is just Newton's law applied to the moving particle, right? And this is fluid, right? And you just, this is a fluid particle. If you follow that, that is called a streamline, right? And streamline, there's a force in two directions. One is okay, and there are two directions. So one is along the streamline direction, or you can say another perpendicular to the streamline direction. And here is along the streamline direction. This is acceleration as, right? And is velocity change relative to the time, right? This is why you use partial derivative, right? Position partial derivative s, that is v, and also dv dt, that is like this acceleration along the streamline. So this is perpendicular to this direction acceleration. Okay. And if you apply Newton's law to this particle, right, this rho as, right, you can look into the pressure difference along this surface, right, dp ds, and there's another force. This is this is gravity-related force projection along this line. This gamma or rho g times sine theta, right? So that is acceleration, right? And the acceleration, you can write this rho d v dv ds. You write in that way. So you do this integration. That is along the streamline. This is Bernoulli equation. Right, so the pressure change and velocity and the g and z is height. Okay, so this is Bernoulli equation, right? So so generally, and you write p plus 1/2 rho v square plus rho gz as a constant, and here the physics behind that is you use Newton's law to this particle or the fluid, right? So the important thing that is this need to follow the streamline. Okay, this only happen along the streamline. Okay, and it's a steady flow and in viscous. Okay, so okay, and we talk about the following streamline, okay, and we also usually in the fluid there are two ways to describe the phenomenon, right? One is Eulerian method, right? Then you basically in this space you take a fixed point, a fixed location. Another way is Lagrange method. You just follow the individual particle, and the individual particle like that is time domain. Just imagine that way. At the time t, this time this particle, right? And we given this small displacement. Given the small time change t plus delta t, this particle shape will change. Right, and this particle shape change can related with the velocity of the particle. And how to understand that? You just imagine that way now. And if you have velocity one dimension, right? This u, right? And then there's small distance delta x, and then the velocity at this point is u plus du dx times delta x, right? This is one dimension, right? So what's the du dx? That mean, okay. And if you think about one dimension, and actually du dx itself is the volume change rate, and And you just imagine that way. Now, if your particle like that way is just a one-dimension motion, with the time going on, the totally this volume du dx times delta x, right, and delta t, right? This is volume change rate. Okay, so this is just one dimension. If you have three dimension, right, and the volume change rate is du dx plus du dv v is another dimension, right, and y dimension velocity. This particle you have x dimension velocity, y dimension velocity. So, and you can also have z dimension velocity, right, w. In that way, du dx plus dv dy plus dw dz, and we write as lambda and v. Okay, that is volume change rate. So what that means? If you have incompressible flow, that means the volume cannot change. If volume cannot change, that is lambda v or du dx plus dv dy plus dw dz equals 0. So sometimes we say incompressible flow lambda v equals 0. That is what it means. Okay, so now come back to streamline again, right? We say along this streamline, and there's a Bernoulli equation already, right? And what for fluid you want to write the streamline function, right? How to write the streamline function? And along this streamline, and you just imagine that way, and streamline here at this point, right? So the dy dx, and this in the direction of u and v and u, this relationship, right? So that is a streamline function, right? In that way, basically, this velocity relationship, you have v, this vector, okay, this is u this direction, v this direction, and this is just the direction, right? Direction dy dx. Okay, so that is the streamline function. Okay, and to visualize that, you can draw that. Let us give one example. You understand what the streamline function. Okay, so here this is a example taken from the first textbook, and if you have velocity field, right? So it's vector, right? And x direction I and y direction j, right? And then this vector velocity you can write in that way, u and v. Okay, so given the u and v and the definition of streamline, right? So you put here and dy dx equal v divided by u, right? You have v and u here. You can write dy dx equal negative y divided by x, right? Then you go through this integration, you find the function along the streamline. That means x times y equals c. So, and therefore, you can draw the streamline function, right? You have x, this x, right? And then you have y. Since xy time equals c, that is streamline. So this streamline, so this is called streamline function. This some words change a little bit. Let me bring this back. So such kind of function we call streamline function, and along this streamline function, it follows this relationship, right? This is psi, okay, d psi dy and equal u, and d psi dx, and this negative equal v, and it automatically follows this relationship. Okay, so this is streamline function. And in fluid, you also learned another function, what we called and velocity potential function. So okay, so and velocity potential, okay, and it's what it mean? Okay, so with this definition, right, another function file, and it's d phi dx equal u x direction velocity, and d phi dy equal vertical direction or another velocity. Okay, so now take this example, right? We already given u and v. Now you plus this one, d phi dx equal like u, right? D phi dy and equal v. You just write the equation from here directly using the definition. Okay, now from this one, you can find the velocity potential function, right? Equal, just solve this equation. You can check, right? So for example, d phi dx, and you will find this is u, right? D phi dy, and you can find this y, right? So that is called velocity potential. Okay, and along this line, we can call the equal potential line, and you draw this. You will draw equal potential lines like this one. So what this mean? Okay, I did this. You see my mouse here. Okay, and let us continue. Okay, so this is along this line, the potential is same, right? This is equal potential line. Okay, and this line will have higher potential than this line, because higher potential is push fluid go this direction. This is streamline, right? This is the potential draw the fluid direction, and the equal potential line and also the streamline actually at each point is perpendicular. Okay, so that is equal potential function. Okay, so this or so that's the potential flow. You guys hear about the potential flow, right? And the potential flow, and actually when we talk about potential flow, it's a velocity potential, right? And then that is used for incompressible, in viscous, in rotational flow. In this class, I didn't explain what's the rotational flow to avoid confusion to you. The only thing is I want to bring the attention to the potential flow. That is potential flow concept, right? There's no viscosity, it's not compressible. Okay. So, and in the commercial software, like you use ANSYS. ANSYS, there are different packages, right? ANSYS Flow and ANSYS Aqua. ANSYS Aqua to solve the potential flow function, right? And in that kind of case, you don't care about viscosity, right? It's just the potential flow. And then in wave energy converter, and one way to solve that is there's WAMIT. WAMIT is software developed by MIT. So WAVE, MIT WAMIT, okay. And this software, if you have buoy in the ocean, you can solve the potential flow function, okay. So, and later we're going to talk about the wave structure interaction, in which you will understand what the WAMIT calculate. They called added mass radiation damping excitation force. Okay, so okay, and again we say this potential flow, this is in viscous flow, there's no viscosity. And another thing is viscous flow. Viscous flow, you have shear force, right? And I already explained this shear force is related with viscosity mu, and or related with rate of shear angle change du dy, right? So, and if you have two-dimensional flow, right, and the shearing not only x direction and also y direction, right? You write in that way. So overall, and for the viscous flow, the equation is more complicated, right? We called Navier-Stokes equation, right? So, and you don't need to remember all these equations. I just try to let you know Bernoulli equation is in viscous flow, right? And also potential flow, we don't consider viscosity or compression of the flow. And the more general case is Navier-Stokes equation, and you can use an NC's fluent to solve Navier-Stokes equation, which address the viscosity problem, and is also consider vortex or kind of non-ideal loss. The only thing is when you use NC's fluent, and the computation time is very long. One small case study, it can take you 1 week or even 1 month, you finally get some result. Okay, so for us, we mostly care about this potential flow. Okay, now, okay, we give some quick review about the basic fluid mechanics. We understand what's viscous flow, invisible flow, and potential function, right? Now, with this background, we are ready to understand the wave dynamics. And this figure shows the wave. Okay, if you have water here, and you have wave motion, right? And there's some concept. This here, you can see this concept. This is wavelength, right? And another thing is the wave height. Okay, and then the peak part is called crest, and this trough. Okay, right? So then this also shows the figure, right? The water motion, the water particle motion, right? Water particle motion, this look like a ideal circle, right? That is for deep water. Okay, what's the meaning of deep water? And deep water means the depth of water is more than half of the wavelength, right? So then there will be some shallow water like here, and the shallow water, okay, and it means the length is much smaller, the depth is much smaller than wavelength. Just give you some number here, and the wave period typically in the ocean is 50 to 150 meters. Right. Therefore, if someone, let us say 80 meters, okay, for such kind of wavelength, okay, and if 40 meters above, that's called deep water, right? So if this water, right, air divided by T20, right, is 4 meters, whatever like that is shallow water, right? Give you sense what means deep water and shallow water. No, okay. Now, and for this, in the next half an hour, we are going to learn the surface wave theory. And the surface wave theory is potential flow function. You can solve this equation. Okay, so this is why we review the potential flow. Here, let us the problem set up. You have water depth, small h, right? And you have wave height 2 times of wave amplitude, right? This is capital H, right? Then you have wavelength lambda, right? And this you also have wave period, right? So how to understand this problem, right? We want to use the potential flow to formulate the problem, and eventually we solve this potential function, that is velocity potential, right? With this velocity potential, and we can d phi dx find the x direction velocity, d phi dy find y direction velocity. Then you understand the velocity, and with this understanding all of velocity, you use a Bernoulli equation, you can understand the pressure. After that, since you know velocity, you can say the particle motion, right? So then in that way, let me say that way, you come here and using the potential flow function, we can find the closed form solution for the wave amplitude, wave period, and particle motion. Another concept is called okay. So and with this we can also understand the wave velocity, right, in the fluid, and how the wave transferred. And details, there are some chapter in this book. And Newman is a professor at MIT. This is very classical book and modern hydrodynamics, and I really like this. And but this textbook, it explains a lot of mathematical equation. If you know math and read the book, okay, there are some chapters to understand that. Okay, so and this problem again, right? This wave amplitude and water depth, wave height, wave amplitude, and this dear water line, and we assume that the surface on the water surface, there's such kind of function, right? And wave function is A is amplitude cosine omega t minus kx. So here the A is wave amplitude, omega the angular frequency was k. Angular frequency was a meaning, it meaning in time domain in 1 second, right? And what's angular frequency? That is what's the mean? Okay, so this is omega, and also the k is wave number. Wave number, it means in 1 meter of one unit. Let us say take the meter example. How many wave period wave the certain wave is? For example, if wave number is 1, that means is 1 meter, you have 1 wave. Okay, this is number of wave. Okay, so here, and the wave number is measured, you say, cycle per unit distance or radians per unit distance. So this is 1 meter, how many radians or how many cycle? Okay. And we often talk about small linear wave theory. What's the linear wave theory? Okay, and there are 2 assumptions. One assumption is small wave. Small wave, that means the wave amplitude h compare. Okay, and the wave amplitude h compare with the wavelength is small, right? Another thing is deep water. Deep water means the wave amplitude compared with the water depth is small. Okay, so with this assumption and this part behind that, there's some mathematical content I skip. Okay, I want to give some very general idea. Basically, you can find the closed form solution. This closed form solution was discovered in about 200 years ago. Okay, and this closed form solution is potential flow, and here the Gaussian equation. Okay, and in compressed flow, d lambda and 2 phi equals 0, right? And then you will have boundary condition, and you have different boundary condition, right? And on the bottom side, the velocity d5 dz, and the physical meaning is vertical direction, the velocity, right? Therefore, on this boundary condition, the vertical velocity will be 0, right? And another is called ecliptic boundary condition, right? And ecliptic boundary condition, this means the particle on the surface will stay on the surface, right? So this ecliptic boundary condition. Then another is dynamic boundary condition. Basically, the pressure on this boundary will be the same. Okay, so under the condition of deep water, right? Here you say this boundary condition is on the surface, is z equal eta, right? And now it changes into surface, and z equal the still water line. There's the assumption. The assumption is the water depth is much larger than the height. So therefore, and this eta compared with the still water line is close enough. So there's simplification. With this simplification, the potential flow or this problem can be further simplified in that way. Okay, so and as I said, if you are a master student or PhD student, you can read the textbook I point out by Newman. You understand it's a very interesting problem. You use a potential flow function plus a boundary condition, you can solve this closed form solution. And for example, here you assume that the potential function and is two dimension. One is x dimension, another z dimension, right? And the still water, the two dimension, x dimension and z dimension. Okay, and the function you say is you assume separation, right? And at a different height, you have fz. This coefficients will be different. Then the wave at a different layer will transmit at the same wave number, same omega frequency, right? So, and using this boundary condition, okay, you can solve this closed form solution. Here, closed form solution here is the potential flow function, and here this is function change with depth, right? Here, this wave propagation at the omega and the wave number kx, right? So using the boundary condition, you can further find the relationship between the wave number k and the frequency omega, right? And so the k is how many cycles per unit length. Omega means how many cycles per time, right? So these two are related. So it's related with here is h function, right? H is water depth. So now, and if you look into wave propagation, you have so-called phase speed. Phase speed here is omega divided by k, right? So you can imagine that way you generate the wave, this will transmit, and this called and phase speed. Okay, so its phase speed is omega divided by k. Okay, so it's a function of the water depth. So now, if water depth is very deep compared with wavelength, right? And practically here, I told you water depth, right? Generally, you have 40 meters like that, or depend on wavelength, right? So it can be 60 meters, right? So, and in such kind of case, and if this kh and in this type of case is very, very large. So tangent kh, right, will become 1. In that case, and the wave number will become omega squared divided by g. What does that mean? Okay, and if you use the relationship k equal 2 pi divided by lambda, right, you can get a wavelength. Wavelength here is 2 pi divided by k, usually k equal omega divided by g. Therefore, use this in the ocean for the deep water, and the relationship of wavelength, lambda, and omega, there's a relationship. And if you have, for example, compare with 10 seconds a wave period, okay, and 10 seconds wave period, and the wavelength difference is 4 times, right? If omega change by 2 and lambda will change by 4, right? So the wavelength can change 4 times, okay. So again, and here the wavelength and has nothing to do with the water depth, right? So in the ocean, you can say it's very deep ocean, right? You have frequency and omega, and you have wave number, the relationship nothing to do with the water depth. And another thing is phase velocity, right? And the phase velocity is here, say omega divided by k. You already get the k relationship. You will find omega c and is g divided by omega. Okay. And the question is now you have long wave and short wave, which one will transmit faster, right? And clearly this relationship, if you have long wave, the speed is higher, right? If shorter wave, the speed is lower, right? So that is for the deep water case, right? And for the shallow water is another case. And here, shallow water H is small, right? H is small, and then tangent H itself, it is can be approximated by k times H. Now, then your k function can be simplified omega divided by gh. Now all the phenomena are different. For shallow water, and as I said, deep water, the wave period has nothing to do with the water depth. And now the function here is water depth. You have shallow water, right? Then the wavelength will be smaller, right? And another is phase velocity. Phase velocity here is also function of h, right? So and in shallow water, right, you have small speed. So that is the potential flow function. That's a closed form solution we got. Okay, normally, and you have intermediate water depths, you can have different expression like that way. So I highlight the red color that you guys get sense, and about wave number, how many cycles, how many radius per length. Okay, and also a wave period means how many cycles per time unit. Okay, this is related. Okay, and when you say this wave in the ocean, you say, okay, there's a wave period you can easily understand, right? And this is, and also wavelength you can understand. But wave what's the velocity? And this is called phase velocity. Okay, so okay, so this is as I mentioned that all this equation, like this closed form equation about the potential flow function, you can solve. This is less than 200 years ago. This is a very beautiful mathematical equation, and you have interest, you really should look into that and learn. Really beautiful equation, right? You can get from the potential flow function, then using boundary condition, you can get this. And with this closed form solution, you can understand the wave number k and wave period omega, this relationship. And the deep water and shallow water will be different. Okay, so now you already get this potential flow function like that, right? So, and we skip the mathematical equation how to get this. The principle is the potential function plus a boundary condition, right? You simplify that. Okay, if you know the surface function A, and then the potential function you can get like this way. So here is depth function. Here is along x direction the wave propagation. So, and as I explained to you, the potential flow function, if you know the velocity potential phi and d phi dx, you can get a velocity in u direction. D phi dz, the two dimension, right? You get z direction, the velocity, right? And now, what's the velocity look like? Okay, so here we normalize the velocity. Any arbitrary position is function of the depth z, right? And it's look like that way. Okay, and you have shallow water. like this one is simplified. Okay, shallow water here, it will be 1. That means if you have velocity shallow water in vertical dimension, and the water particle velocity will be the same, right? Okay, and if you have deep water, it's different, right? Deep water at the surface in horizontal dimension, and the amplitude is larger, right? With the time going on and deep and then the water here, the velocity is smaller. Okay, so about z dimension, and z dimension is velocity we can also normalize, and in the shallow water, and is almost linear relationship, right? So velocity in vertical dimension at the surface large, and with the time going on, the surface is amplitude vertical dimension is small, and also the deep water is EKZ relationship, right? So also the water depth with the time going on, the vertical dimension they change quickly. Okay, so this will give you some sense about the vertical particle velocity of the vertical dimension. So for example, you know the surface, the amplitude, right? Here, A amplitude is the surface motion. Okay, with the time going on, the different this wave will transferred, right, in x dimension, in x direction and z direction. However, the amplitude will change, right? And you with deep water, right? You have z equal depth of half of wavelength. For example, the wavelength 80 meters, half will be 40 meters. And how large the velocity will change. You put this relationship, you will find, okay, the whole number, if you go to 40, let us say wavelength is 80 meters, at lambda, at z equal lambda divided by 2, 40 meter wave, 40 meter depth, and the amplitude of the particle motion reduced to 5%, right? And at a quarter of wave, quarter depth, and that has become 23%. So I want to give you a number, put this in your mind, and the surface wave or water wave is surface wave. Surface wave is on the surface, right? And with the time going on with deep water, and then the motion is very, very small, right? As I mentioned to you already, right? And if you go to the water depths, and half wave period, half wavelength is already reduced to 5%, right? Now, so suppose wave amplitude, wavelength 80 meters, if you have z equal 20 meters, the amplitude reduced to about a quarter, right? So give you a sense this surface will quickly decrease. Okay. So now we get sense about the surface wave, the amplitude decrease very quickly, right? And deep water and shallow water, the amplitude like that way. And then we put an idea about the surface wave concept, the amplitude decrease quickly. So now we